Okay, Math 8 students, here we go with lesson 3.2, rate of change and slope. Starting out again with a little key vocabulary, we have the term rate of change. Rate of change is the ratio of the amount of change in the dependent variable, or the output, we also know that as y, to the amount of change in the independent variable, which we usually refer to as x. So it's a ratio of the rate of change of y over x. Rates of change can be constant or variable. Constant rates of change, when you graph them, will make a straight line. Variable ones will not, which is what we've got down here. Constant rates of change as a graph will make a straight line. Variable rates of change will not graph as a straight line. So what we're going to do is we're going to go ahead and move into the first practice problem, which is identify rates of change and tell whether it is constant or variable. So what we do when we're identifying rates of change is we are doing exactly what it told us up here. We're going to compare the ratio. We're going to look at the ratio of the amount of change in the dependent variable, which we need to identify, and the amount of change in the independent variable. So first thing we want to look at here is we've got a table, and this table is showing that Eve keeps a record of the number of lawns that she has mowed and the money she has earned. Tell whether the rates of change are constant or variable. So what we're going to look at is we've got number of lawns and amount earned. One of these is our dependent variable, one of these is our independent variable. So one of them is the input, one of them is the output. That might make it a little bit clearer. We're putting in number of lawns mowed, right? So that's going to determine how much money we earn. So this would be our x value, our input, our independent variable, and the amount earned would be our y value. That's going to depend on our number of lawns mowed. So what we're going to do now is we're going to go ahead and compare each of these ratios. So we're going to look at our change in y over our change in x from day 1 to day 2. So day 1 to day 2, we're looking at $15 earned. Oops, let's go ahead. I need a little more space here. So what I'm going to do is I'm going to make a little subtraction problem here. I'm going to look at my y variable over my x. So I'm going to have $45 earned on day 2, and we're going to see the change from day 1 to day 2. And then I'm going to put that over the number of lawns mowed. Okay, so I've got my day 2 values here and my day 1 values here. I'm looking for the change in y and over my change in x. And this is going to give me 45 minus 15 is 30, and 3 minus 1 is 2. That simplifies down to 15 over 1, or 15. Okay, so now I'm going to compare that to my day 2 to day 3. So I'm going to set it up the same way. I'm going to put my day 3 variables here. My dependent variables go on top, and on day 3, I didn't make it. Eve made $90, and she mowed 6 lawns. And then on day 2, she made $45, and she mowed 3 lawns. So here I've got my change in y values, my change in money, and my change in x values. So I'm going to go ahead and subtract here. 95 minus 45 is 45, and 6 minus 3 is 3. That's going to go ahead and simplify down to that 15 over 1, or 15. So far we're looking like we have a constant rate of change. We're going to just go ahead and finish out this table comparing day 3 to day 4. So again, I'm going to compare my y and my x values. So looking at day 4's values, I have $120 minus $90 from day 3. Looking at that change from day 4 to day 3, she mowed 8 lawns on day 4, and she mowed 6 lawns on day 3. So we're going to look at that change here. So 120 minus 90 is 30. and 8 minus 6 is 2. So I'm going to simplify that down, reduce that down, and I have 15 over 1, or 15. So all of my ratios here of my dependent variable to my independent variable are all 15, or 15 over 1, which means she's making $15 per 1 lawn. So my rate of change is my ratio of y to x, which is $15 to every 1 lawn, or 15. So that would be my rate of change. And we're going to go ahead and just write that down as it compares to what we're actually looking at here in this problem. So that would be $15 per lawn. Because it's great to be able to find the numbers, but we also need to know how to apply it to the question that is being asked. And this, is it variable or constant? Well, we have 15, 15, 15. It does not change. That would be constant. If we were to graph this, it would be making a straight line as well. Okay, so let's go ahead and come down here to your turn. And what I want you to do is go ahead and pause the video. I want you to go through this and try it, and then when you have finished it, go ahead and press play, and you will you can see if you did the answer or did the problem. Okay, so hopefully you paused the video, you took a little bit of time to solve this question and determine if this rate of change is constant or variable. So the table shows that the approximate height of a football after it is kicked. Tell whether the rates of change are constant or variable. Sometimes what we'll be able to do is we'll be able to just look at this question and be like, well, a football doesn't move at a height that is constant, but we're going to go ahead and take the data and look at it anyways. So we're going to compare our values, and this is going to be our x variable. This is going to be our y variable, and we're going to compare our y values to our x values. So let's go ahead and take a look at, I'm just going to go ahead and give these numbers here. So this is x1, x2, x3, x4, y1, y2, y3, y4. So I'm going to go ahead and set this up so that I'm looking at my y2 values, or my y2 value, which is 18 feet, minus my initial, which is 0. And then I'm going to set this up here with my x values on bottom, which is 0.5 seconds minus 0 seconds. So I've got 18 over 0.5. Okay, and I can go ahead and simplify that down, but I'm going to leave that there for now and just go ahead and move on to the next one, comparing my y and x. And a lot of times you'll see change in y over change in x written this way. That little triangle, that means change. That's what that means. So I'm going to look at my y3 value, my height, my third height, which is 31 feet, minus my second height, which is 18 feet. And I'm going to compare that to, I'm going to make that as a ratio of time. So my x3 value, my third time value, is 1.5, minus my x2 value, my second time value, is 0.5, or 5/10. And I'm going to subtract that out. So 31 minus 18 is 23. No, sorry, 13. I can do math. And 1.5 minus 5 is 1. Okay? So what I can do here is I'm just going to backtrack a little bit. If I don't like this decimal, I can go ahead and multiply each of these by 10 or by 2 to get a whole number, right? So 10 would be moving the decimal over 1, and it would be 180 over 5. Or I can go ahead and multiply them by 2 because that's going to give me a whole number here on bottom. And that would be 36 over 1. So now we have a ratio that is over 1 to compare to. Okay, sorry, little tangent there. Let's go ahead and compare that third set of values. We got our change in y values over our change in x values, and our fourth height, which is 26, minus our third height, which is 31 feet, over our time values. Our fourth time value is 2, minus our third time value, which is 1.5. So I can already tell that this is going to be a negative value here. This is going to be what? Negative 5 over 0.5. And again, if I want to turn that into a whole number value, I'm going to multiply this by 2. And that's fine, because as long as I create an equivalent ratio, as long as I'm doing the same thing to the bottom and top number, the numerator and denominator, then it's okay. It's just an equivalent ratio. And this is going to be negative 10, and this is going to be 1. So I'm going to look at these ratios now of my rate of change. And this one here, what this basically means is 36 feet per 1 second. This is 13 feet per 1 second, and this is negative 10 feet per 1 second. And what that means is if we're measuring height, this means it went down. So negative 10 feet per 1 second. So our rate of change, we don't have a singular rate of change, do we? So rate of change is variable. If we were to graph this, let's go ahead and just make a rough little graph. You don't have to write this down, but it's, if you're a visual person like me, it kind of helps. And this would be our height, and this would be our time. So at 1 second, it would be 0, and then it would come up like this, right? And then it would come back down. And so we can see that our rate of change does not make a straight line. So we don't see that nice straight line here, which would indicate a constant rate of change. What we've got is this curved line, and that is a variable rate of change. Okay, let's go ahead and move to the next topic. So we've got slope. And slope is when the rate of change is constant. That's the term we've used. When the rate of change is constant, any segment of its graph has the same steepness. Oh, got a little typo here. Its graph has the same steepness. The constant rate of change is called slope. So here we go. We've got a constant rate of change. It is a straight line. And we can also think of this as the average rate of change, right? So we find slope by determining the ratio of the change in y values, rise, we call that rise, which is right here, for a corresponding segment, so meaning from here to here, right? This would be between 2 points of a graph in the change in the x values for the run. So slope in a nutshell is rise over run. Just like we were doing, subtracting y2 values, subtracting y1 values from y2 values, and then subtracting x1 values from x2. So slope, we use m to abbreviate. I should put that in here. Slope is m. I don't know why. It just is. And slope is rise, change in y values, y2 minus y1, change in y values, over run, which is our horizontal values, which is our change in x. So our change in x values and our change in y values. That's what we're looking at with slope. Hopefully that doesn't look too complicated. So we're going to go ahead and try this now. So we've got a graph, and we're looking at these 2 points on this graph. And what it wants us to do is choose 2 points on the line. Well, I already just chose them for us. They've been nice and determined for us. We could pick any 2 points, though, if we wanted, and the slope would be the same, which is kind of neat. And then we've got this little reminder up here. If you move up and right, your slope is positive. If you move down and left, your slope is negative. So we are moving down and left. This means that this is a negative slope. So we can go ahead and just take a little bit of a tangent over here and talk about types of slope. So this would be a positive slope. It's like you're going uphill, up and right. And they can be in any quadrant. I'm just drawing single quadrant right now for sake of space. This would be a negative slope because you are going down and left, downstairs. Upstairs positive, downstairs negative. And then we have two other types of slopes that you want to keep in mind, and that would be a zero slope, which is a flat slope, 0. And you have a undefined slope, which is straight up and down. So again, positive slope, negative slope, zero slope, undefined slope. Those are important little ones to remember. Oops, let's go ahead and just move this down here for now. I'll move it over here. So we're going to choose, going back to our try it, we're going to choose 2 points on the line, and I went ahead and picked these red ones right here. And then what we're going to do is go ahead and write down those points. So this point here, and we always put our x value first. So point 1, x1, comma, y1, and point 2, x2, comma, y2. So we're going to go ahead and call this point 1 and point 2. I take that back. We're going to switch those, just for making things a little bit easier down the line. Call this point 1 and this point 2. So the point value here for point 1 is what? Our x value is -6 and our y value is 4. Here for point 2, our x value is -1, 2, 3, and our y value is 1, 2, positive 2. So we've got points -6, 4, and point 2, -3, 2. Okay, now that we have points, we're going to determine our change in y values, which is our rise. So change in y would be y2 minus y1. So we're looking here, y2 is 2 minus y1. So y2 is, let's see, maybe I'll write these up here for you. This is x1, y1, x2, y2. So y2 is 2. So 2 minus 4, which is -2. And that makes sense because we are going down. Our rise, it's kind of, rise you think up, but rise is your horizontal distance. We are going down for that horizontal distance. So our rise is -2. And our run, which is our x values, we're going to take our x2 value minus our x1 value. x2 is -3 minus -6, and remember when you are subtracting a negative, you are actually adding, so this becomes -3 plus 6, which is 3, which makes sense because we are moving in a positive direction here. So we've got our change in y over our change in x, just like our rate of change, and that is going to be -2 over 3, which means we are moving down 2 and right 3 every time. So does that make sense? We're going to double check that. We're moving down 2 and right 3. Would it be the same for another point? Down 2, right 3. Yep, we got there. Let's go ahead and check again. Down 2, right 3. Down 2. Okay, so you see what I just did there with the graph? You can determine slope from the graph. You got to find those intersection points and then count your change in y values. If you're going down, it's negative over your change in x values. Okay, so we got to go ahead and try one on your own. So what I want you to do here is go ahead and pause the video and try it on your own, and then once you've solved it, go ahead, press play, and see if you solved it correctly. Okay, so hopefully you paused the video and worked on this question here, your turn number 4. Let's go ahead and take a look at that. The graph shows that the rate at which water is leaking from a tank. The slope of the line gives the leaking rate in gallons per minute. So that's our unit right there, gallons per minute. So let's go ahead and we're going to take a look at this graph. And we've got a couple points marked here. First, let's identify the units that we're working with. We've got, looks like we're going by 1 minute. And same here, looks like we're going by 1 gallon. So it's leaking at a rate of, if it is 4, we'll take a look at this point. We got 4 minutes. And at 4 minutes, it has leaked 3 gallons. Okay, so that's the value for this point here. X is 4, Y is 3. 4 minutes, 3 gallons have been leaked. Then we're going to take a look at this point right here and find that X and Y value. And it looks like 5, 6, 7, 8. At 8 minutes, 6 gallons have been leaked. Let's go ahead. I'm just going to write that a little bit bigger. So 8 gallons in 6 minutes. So what we can do here with a graph is we can use our rise and our run with our formula where we have our change in y over our change in x, which is our y2 minus y1 over x2 minus x1. This would be our x2, y2, x1, y1, or the simple way with a graph is we are actually just going to count our rise and run. So we're going to look at our rise, which is up how many units? 1, 2, 3 units. We go from 3 to 6, right, which is right here. 3 to 6 is our difference in y. So our change in y is plus 3, which is what it's looking for over here. Our rise is plus 3. And then our change in x, if we count our run, we're going to go horizontal. From here to here is 1, 2, 3, 4, which makes sense with our point values. Difference of 8 minus 4 would be 4. So that is our plus 4. So rise, we go up 3 and over 4. Now, just a little tangent here, something to think about is that when you are counting units on a graph, you need to make sure what your values are that are being measured. We can count up 3 and over 4 because each unit here is 1. But we want to make sure that we're not counting by 2s or counting by 4s to make sure that we're getting an accurate slope. So the rate at which water is leaking is 3 gallons per 4 minutes. Did you guys get that? 3 gallons per 4 minutes? So you could write this as m, which is slope, equals 3 over 4. And if we were to graph that, we would just want to, we can double check that. Up 3 over 4 to that point, up 3 over 4, up 3 over 4 to the point that is off the graph. And we are going up and over to the right, so this is also a positive slope. And just to tie in some previous values here, we know that it is proportional because it goes through the origin. It's a straight line through the origin, so just tying in some previous concepts there. Okay, let's go ahead, and the next thing that I have for you guys is a bonus activity. If you want a little bit more practice using graphs to find rates of change, this is an optional activity. You don't have to do this, but if you want more practice, this is what we're going to do now. So you can go ahead and stop and be done with notes if you want, or you can go ahead and watch this part and do a little bit more practice using graphs to find rate of change, which is constant rate of change, which would be slope. Okay, so using graphs to find rates of change. You can also use graph to find rates of change. We did talk about that already, but we're going to go through a little bit longer of an explanation now. So the graph shows the distance that Nathan biked over time. What is Nathan's rate of change? Find the rate of change from 1 hour to 2 hours. So here we are again. We're using multiple values. So this is our first value, second value, third set of values, and fourth set of values. So the nice thing about the graph here is that we can just count our units. We know this is a positive slope, but we are going to go ahead and also check with our slope formula, which is our change in y over our change in x. So we're looking at our first two. So from 2 hours here, This is our x2 and y2. This is our x1 and y1. So 30 would be our second y value. 30 minus our first y value is 15, because that is from 2 hours to 1 hour. We've got to put it in backwards. So 30 minus 15 is 15. From 2 hours to 1 hour is 1 hour. So how many miles were rode per hour? 15, if we simplify that. 15 miles per hour. Okay, so here to here is a constant rate, straight line. Let's go ahead and check and make sure it's still a constant rate from hour 2 to hour 3. This is our x3 and our y3. And this is just kind of some bonus information here, just thinking for the future when we're doing values with y and x. So change in difference from 1 hour to 4 hours. So here's 1 hour. Here is 4 hours, right? This is our x4 and our y4. Our fourth y value, our fourth x value. So 4 hours we had 4 hours we had 60 miles, right? And at 1 hour we had only gone 15 miles. So at 4 hours minus 1 hour, we have what? 45 miles in 3 hours, which simplifies to 15 miles per hour. So same constant rate of change here. And then we're going to go from 2 hours to 4 hours. So from 2 to 4. So 60 miles minus 30 miles gives us 30. And 4 hours minus 2 hours gives us 2. If we simplify this down, our rate of change is 15 miles per hour. So all of these here are constant. So we have a constant rate of change. Now let's go ahead and just take a look at the graph, because there is other ways to do this, and I'm going to use a couple different colors here just to illustrate. So for this change here, this first change from 1 to 2 hours, from 1 to 2 I am going, remember I'm checking my units here, these are up by 5, so this is one of the moments where you want to make sure that you are counting using the correct values, because I'm going up 3, but that 3 is actually 15, so up 15. And then the values here are 1 hour at a time and over 1. Does that make sense to what I found here? Yeah, 15 miles per 1 hour. Okay, so this makes sense. And then I'm going to go ahead and look at my second one here, from 1 hour to 4 hours. And so I go up 45, right, and over 3, which matches what I have here, and simplifies down to the same thing. So what I'm doing here is I'm counting values on the graph instead of subtracting values from our points. Okay? So then I'm going to go ahead and take a look at this last one from 2 to 4 hours, and it should look the same as some of the other ones, right? It should simplify down the same. I'm going from 2 hours to 4 hours. So from 2 hours, I'm going up 30, which is my change in y, and over 2. Now up 30 and over 2 matches the values I have here, so I just found the same thing in a different way and simplifies down to that 15 miles per hour. So 2 methods here. I can count the units and simplify, right? Count the units, simplify, works the same way, essentially what I'm doing here. Count the units, simplify, works the same way, and then count the units and simplify. Works the same way as this here. So 2 methods. If you're a visual person, you might just want to use the method of counting units on the graph, but again, do make sure that you are counting the correct amount of units, not 3 squares, 15 miles. And we're going to take a look here at these questions now. We're going to reflect. Or recall first that a graph of a proportional relationship is a line through the origin. Explain whether the relationship between Nathan's time and distance is a proportional relationship. Well, what do you think? Do you think it's a proportional relationship? I would say yes. And the reason it is, you can look at a graph, you can look at this graph, and it is a straight line that goes through the origin, meaning at 0 time he has gone 0 miles. And then he travels up at a constant rate. So yes, it is proportional because the graph is a straight line through the origin. You guys can just fast forward through the time it takes me to write this down. Straight line through. And again, the origin is that 0, 0 value. When x is 0, y is 0. Okay, now let's go ahead and reflect. We're going to make a conjecture, which is kind of like making a prediction. What do you think is going to happen? Does a proportional relationship have a constant rate of change? Does it? Yes. It has to if it's going to make a straight line. So proportional relationships have a constant rate of change. I'm just going to put a couple little notes here. A constant rate of change whoops, I'm just marking all kinds of things up, equals a straight line. And a proportional relationship has to have a straight line through the origin on a graph. And the whole idea is that a proportional relationship, everything will simplify down to the same rate of change, the same ratio. All right, the last little reflection we've got here is, does it matter what interval you use when you find the rate of change of a proportional relationship? Explain. So 2 parts here. Does it matter? It doesn't matter what interval you use. If we go back here and look at this graph, we used 3 different size intervals. We used this interval here of 1 hour, we used this interval here of 2 hours, and then we used this giant interval of 3 hours. So it didn't matter what interval we used as long as we were consistent with the values that we were using. So no, it does not matter. And now we're going to explain that. In a proportional relationship, the rate of change is constant. Go ahead and just skip forward while I write this down. Relationship. The rate of change is constant. Meaning that everything should simplify to the same ratio. All values should simplify to the same ratio. And that ratio is called our what? Constant of proportionality. Or K. And in this case, the constant of proportionality can also be M, which is slope. Okay, that's it. If you did the bonus activity, you've been listening to video for a long time, please go ahead and shut down, and I will see you tomorrow. Remember, if you have any questions, please write those down and bring them in, and we can talk about them either one-on-one or in a small group in class.